right, in this video, we're going to be taking some notes on permutations and combinations. And this is some new vocabulary. So first, we're going to talk about what this is. Permutations. Well, if you select some items out of a group and the order of the items in your selection is important, then your selection is a permutation of the group. So that's the definition. Let's look at an example. For example, suppose we have Anna, Bob, Cal, and Dan enter a local essay contest. Here are some possible ways for the judges to select the first prize and second prize winners. So that's what's going on in our chart here. So we could have Anna in first place and Bob in second place. So I'm going to call that AB. That's Anna Bob. So over here it says Anna Bob means Anna is in first and Bob is in second. Well, we could also do Bob Anna, which means that Bob is in first and Anna is in second. And that one was down here. But what else could happen? Well, we could have Dan come first and then we could have Cal come second. Or we could have Cal come first and then Dan come second. So we could go through and we could make a list of all the different ways that we could award first and second prize. So let me just pause for a second here while I write them down for you. So when I'm doing this kind of thing and listing them out, to me it makes sense to do them sort of in order. These are all the ways Anna could come first. These are all the way Bob could come first. These were all the ways Cal could come first. And these were all the ways Dan could come first. If I added all of those up, I'd have a total of 12 different first, second groupings. That's called a permutation, or I would have 12 permutations. In a permutation, the order of the names is important. Anna Bob is different than Bob Anna. We have a math formula. The number of permutations of n items of a set of arranged r items at a time is given by this formula. NPR is equal to n factorial over n minus r factorial. Factorial is this little exclamation point. It means a whole lot of multiplications. We're going to use our calculator to do this for us, so we're not going to worry too much about the formula because the calculator has a permutation button for us. So let's try to answer the problem without making a list. It says, in how many ways can the judges select the first prize and second prize winners in the essay contest described above? So the first thing we're going to do when we're solving any of these counting kind of problems is we're going to decide, is the order of the names important? And the answer to this question is yes, because Anna Bob is not the same as Bob Anna. So that's what tells us we want to do this permutation that I had up here. So the next thing we're going to have to do is step 2. In step 2, we've got to figure out what this N and the R are in this NPR formula. So N is right here. There are 4 people in the group of contestants, so N equals 4. N is the total number of objects, in this case people. Okay. Then we have the R. Okay. There are 2 people that we're going to choose when we're giving out the prizes, so that means R equals 2. And R I'm going to call the number selected. So since we have a big group and we're selecting some of them, realize that N always has to be bigger than the R. So then we're going to put this into our formula, and this was our formula. It went NPR. So our N was 4, so I'm going to start with a 4, and then I have the P, which stands for the permutations, and then I have my R, which was 2. And this is what I'm going to do to put it into my calculator. So we have a couple different kinds of calculators that we use. So first of all, I'm going to pull up a picture of the TI. I don't have a TI that works, that I can push the buttons on, but we can use the picture and see how it goes. So if I were using my TI, where I'd find the permutation button is I'd start out and I'd hit the math button, and then I would hit the over arrow 3 times until I got over to the one that said PRB up at the top. And then the second item down is NPR, that's permutations. And by the way, we're going to use this one also today. The third button is NCR, that's combinations. Okay, so I started out, I hit math, then I hit the over arrow a couple times until I got to probability, and then I selected number 2 for NPR. All right, if I had my Casio calculator, I would be just in the regular run menu, and I want to hit the option button, and then I hit the over arrow, the F6, until I get to prob, and then I have NPR or NCR. Let me clear those out. That's where I would get the P. Now, before I can do this, I need to be sure I would actually have the 4 in there first, because it goes 4, then the P, then the 2, and I hit enter, and I get 12, which was the number of permutation. So you might want to write down these calculator steps on your paper. I had written them down for the TI. Again, for the Casio, we hit option, then we hit F6 for more options, and then we hit F2 to get the NPR. For the TI, I'll just write them in here. We hit math, then we hit the over button a few times until we got to PRB or probability, and then it was number 2, NPR. Okay, so you'll need to be able to do that on whatever calculator that you're using. And that's what we got down here on the bottom. There are 12 ways for the judges to choose the first and second prize winners. Okay, now to the next part. The next one is combinations. So if you select some items out of a group and the order of the items in your selection is not important, then your selection is a combination of the group. So what would this look like? For example, suppose Anna, Bob, Cal, and Dan enter a local essay contest again, but this time we're looking for 2 finalists who will go to the statewide essay contest. So here are some ways for the judges to select the contestants who will go on to the state contest. So we could say, I want Anna and Bob to be a finalist. Well, Anna Bob means that both Anna and Bob go. I could have Dan and Cal selected as my finalist. That's different than my first choice. If I chose Bob then Anna, Bob and Anna still means that both Anna and Bob are going. So these 2 things are the same if I'm just choosing 2 people to send to the competition. So if the order of the names is not important, that's what makes this a combination. So let's look if I were to list this out. So when I say who comes first, and I say it could be Anna Bob, or it could be Anna Cal, or it could be Anna Dan, when I go down to choose, well, what happens if Bob comes first, I'm not going to write Bob Anna because I already used that with Anna Bob. So I could have Bob and Cal, or I can have Bob and Dan. Then I could choose Cal comes first. Well, I'm not going to have an Anna second or a Bob second because I've already done those. The only option is to add on Cal and Dan. So how many ways do I have here? 1, 2, 3, 4, 5, 6. Only 6 choices this way. This is called 6 combinations because the order of my little group doesn't matter. I have a formula that I can use if I get more complicated with the number of combinations, again, of n items chosen r items at a time, is this formula, which looks pretty similar to the other one, except for we've added a little more on the bottom, which makes our group smaller. But we'll use our calculator to do it. So let's read this. In how many ways can the judges select the finalist who will go to the state contest? First thing we're going to decide in all of our problems is the order important? Our answer is no. If the order is not important, that tells us we're looking for a combination. Next, we're going to describe the N and the R. Just like before, N was the total size. There are 4 people in the group of contestants, so N equals 4. And N was the total number of objects. Then I need to choose R. R has to be smaller or equal to because this is the 2 people who are chosen in each selection of contestants that are going on to the state. So R is 2. R is the number of objects that are chosen. Okay, then I'm going to put each variable into our formula. Again, the bigger number has to come first, so we're doing 4C2. So I'm just going to do this on my Casio calculator because that's easier to show, but it would be the exact same thing if you were doing it on your TI calculator. Oops, sorry, I popped that up and it was gone. I need to start out, I need to type the 4 first. Now, assuming I had cleared everything out, let me exit way back to the beginning. I would hit the 4 first, and then I would go to Option. I would hit F6 for more options and go to Probability, and this time I need the NCR. If I were using my TI again, I would go to Math, hit the Over button to get to Probability, and choose the NCR button. And then I hit the 2, and you can see my calculator knows that 4C2 is 6. So there are 6 ways for the judges to choose the finalist going to the state contest. There's a statement down here that's really important. In permutations and combinations, I wrote and combinations twice, sorry. Once an object is chosen, it cannot be chosen again. We can't choose Anna twice. We can't choose Bob twice. In permutations and combinations, once you choose an object, it's no longer in the pool of objects you can choose. We often call this without replacement. We're not replacing the objects back into the original selection. Okay, so let's turn the worksheet over here and try some more examples. All right, we also have the counting principle. You guys have been working with the counting principle for a long time, starting back in middle school and elementary. So sometimes there's more than one type of object being selected in a problem, or an object can be selected more than once. The counting principle is used to determine the number of possible outcomes for an event found by multiplying the number of choices at each stage. So what does this mean? Let's look at problem 3. We have a summer camp that offers a choice of swimming, tennis, or basketball in the morning, and gymnastics or crafts in the afternoon. So how many different pairings of one morning and one afternoon activity can be scheduled? So in this case, I'm not just randomly choosing a group. I'm going to do 2 things. I'm going to choose something for the morning, and then I'm going to choose something for the afternoon. Those 2 choices are not related to each other, so that means I'm going to use this counting principle and I'm going to multiply them together. So how many ways can I choose what I do in the morning? Well, I have 3 different items, and I'm going to select one of them. So that's 3 combination of 1, because the order in which I choose them, swimming, tennis, or baseball, isn't going to matter. Whenever there's only one object, it would be the same thing if you did a combination or permutation because there's no real order. Okay, so I have 3 combinations and I'm going to choose one of them. Then in the afternoon, I have gymnastics or crafts. So I have 2 activities and I'm going to choose one of them. Now I'm going to need to go to my calculator. So I have 3C1, which is 3 because those were the 3 things I could choose. I have 2C1, which is going to be 2 because there were only 2 things I could choose. So I have 3 ways to choose the morning times 2 ways to choose the afternoon would be a total of 6 different schedules. Okay, let's do another one. Problem 4. Applebee's is running a special family meal deal. So you have your choice of 2 of 5 appetizers. So we can choose the mozzarella sticks, the bruschetta, the chicken fingers, the potato skins, or the chips and salsa. So after our appetizers, we're going to choose 2 of 4 entrees. There's pasta, chicken, beef, or shrimp. And then the family gets to choose 1 of the 2 desserts. Whoops. Either ice cream brownie sundae or apple crisp. So we want to know how many different meals are possible. So here we need to make multiple choices. First, we have to choose our apps. What I choose for my appetizer is different from what I choose for my entree. And then after I choose my entree, I'm going to choose my dessert. Since all of these things are independent of another, what I choose for one doesn't affect the next, I can multiply these values together. So now I've got to decide how many ways can I choose the appetizer. Well, there's 2 of 5 appetizers that I'm going to choose. Would the order matter? Does it matter if I tell the waiter I want mozzarella sticks and bruschetta or bruschetta and mozzarella sticks? No, it doesn't. I'm going to get them both. So this is going to be a combination. I'm choosing 2 of 5, but remember, 5 is the total number of objects and 2 is how many I choose, so the 5 has to come first. I'm going to take that and I'm going to multiply it by my entree selection. Does it matter which entree I choose first? No, so that's a combination as well. I'm going to choose 2 out of 4 entrees. The 4 is the bigger number. It has to come first. There are 4 total entrees. I'm selecting 2. Then for my dessert, well, there's 2 desserts, and I'm going to choose one of them. Now I can go to my calculator because I don't know what 5C2 is. So I type the 5 first. C2 is 10. So there's 10 different ways I can choose the appetizer. Then I'm going to choose my entree. There's 4 C2 ways to choose my entree. So there's 6 different ways I can choose my entree. Then I'm going to choose my dessert. There's 2 C1 ways to choose my dessert. So there's 2 different ways I could choose dessert. So each of the 10 appetizers could go with each of the 6 entrees, which could then go with each of the 2 desserts. So 10 times 6 times 2 is 120 different meals that I could choose. All right, so we have some additional examples here that we're going to try. And we may need to pause the video to write stuff down. Sorry, I didn't mean to pop my calculator up just then. Okay, so I resized so I can just leave my calculator up there. It says, tell whether the problem asks for permutations or combinations, and then answer the question. So number 1 says, how many ways can 4 posters be arranged on the wall? So to decide if we want a permutation, that's when the order is important. And in a combination, the order is not important, right? So what do we have here? If we're arranging the posters on the wall, if we're arranging them on the wall, it's going to matter which poster I put first, second, third, and fourth. So if the order matters, then we're looking for a permutation. And I have to say, how many total objects do I have? Well, I have 4 posters. So the 4 comes before the permutation. Then I have to decide how many posters I'm going to choose to arrange. Well, I'm going to choose to arrange all 4 of them. So what I have is 4p4. I'll put that in my calculator. Oops, I can't. By the way, I got a math error right there, and it's a good thing for me to show you. You see, the reason I got a math error is because my second number was bigger than my first number, just by accident, and I'm not allowed to make the second number bigger than the first number. So let's get that out of there. So what I really wanted was 4p4, and the answer is 24. So there's 24 different arrangements that I can put the posters in. All right, number 2. How many groups of 4 posters can be chosen from 7 posters? So in this one, if I'm just selecting a group of posters, I'm at a store and there's 7 posters, and I'm going to choose 4 of them to purchase. Does it matter which poster I choose first and which poster I choose second? Not so long as I'm taking all 4 of them. So that means this is going to be a combination problem. So I need a C when I'm using my calculator. It also means that I'm going to have fewer options available. So the first number is the total number of objects, which there's 7 posters at the store. And then the smaller number comes second. There's 4 posters that I'm selecting. So I need 7C4, so I'm going to get that into my calculator. And 7C4 is 35. So there's 35 different groups of 4 posters each that I could choose. All right, number 3. A high school assigns each student a 4-digit ID numbers using the digits 0 through 9. Digits may be repeated, but the first digit cannot be 0. How many ID numbers are possible? Well, in this one, I'm not just, I don't have a group of numbers and I'm just choosing one out of it. And once I choose to use the 9, I can't use it again. If that were the case, then it would just be a straight up permutation or combination problem. But in this one, in essence, what I'm doing is I'm choosing the first digit. Then I'm going to choose the second digit. Then I'm going to choose the third digit. And then I'm going to choose the fourth digit. Each of those choices is going to be multiplied together because in this case, what I choose for the second digit is not dependent on what I chose for the first digit. I can repeat numbers. So we have to look at how many ways I can choose each of those. Well, my first digit cannot be 0. So my first digit right here is 1, 2, 3, 4, 5, 6, 7, 8, or 9. So my first digit, there are 9 numbers, and I'm going to choose one of them. So in my calculator, I'm going to do 9, choose 1, which hopefully we've realized is just going to be 9. There's 9 choices I could have made for that first number. Then I get to my second digit. Now my second digit could be a 0 through a 9. 0 through 9 is really 10 digits. So I have 10 digits and I'm going to choose one of them. I could put this in my calculator if I didn't realize that it was just going to be 10. Now I go to choose my third digit. It doesn't matter what I chose for the other two. I'm still going to have 10 ways to choose the third digit and 10 ways to choose the fourth digit. That's because I'm replacing each of those numbers. I'm allowed to choose them more than once. So I have 9 times 10 times 10. If you're being particularly lazy, you could type it into your calculator. Hopefully you would realize we're just going to stick 3 zeros on the end of the 9. So 9 times 10 times 10 is 9,000. All right, I'll do one more and then I'm going to make you guys pause the video while you try them on your own. All right, Bill has 3 hats. He has 5 shirts. He has 10 pairs of pants. And he has 6 pairs of shoes. If an outfit consists of a hat, a shirt, a pair of pants, and a pair of shoes, how many different outfits does Bill have? Well, we've got to decide, are we dealing with combinations or permutations? In this case, it's not necessarily going to matter. If we're choosing just one hat, it doesn't matter if we choose it in order or not. So we could really go either way with this one. But the first thing we're going to do is we're going to choose our hat. How many ways can we choose the hat? We've got 3 hats. I'm going to choose one of them. So there's 3 ways to choose a hat. For my shirt, I've got 5 shirts. Of the 5 shirts, I'm going to choose one of them. So there's 5 ways I can choose my shirt. Then I've got my pants. I've got 10 pairs of pants. I'm going to choose one of them. So there's 10 ways to choose the pants. And last, I'm going to choose my shoes. I have 6 pairs of shoes. I'm going to choose one of them. So there's 6 ways to choose the shoes. What I choose as a hat and a shirt and a pants and a shoes are all independent of each other. So to figure out what I need, I'm going to multiply all 4 of these numbers together to get my total number of outcomes. 3 times 5 times 10 times 6, there's 900 different outfits that Bill could choose. Okay, let's read the next one and decide where we are, and then we'll pause the video while you guys try to figure it out. A team plans to choose 3 of the colors represented in the 5 rings of the Olympic flag for team uniforms. Colors are blue, yellow, black, red, and green. How many different 3-color combinations can be chosen? So I see the word combination in here, which is a little bit of a clue. But a locker combination is really a permutation. So we got to be careful. The order matters in some things. So think about the problem. If I'm choosing 3 colors to use for my uniforms, is it going to matter what 3 colors I choose? Does it matter if I choose the blue and the yellow and the black, or the black and the yellow and the blue? No, it doesn't. So this is going to be a combination. So go ahead and pause the video while you try this one, and then we'll see how it goes. Okay, so that was a combination. There were 5 total colors. I chose 3 of them, put it in my calculator, and I got 10. We're going to go ahead and turn the paper over to get the rest of our example. Scratch that. You don't turn your paper over. It keeps going all on one page for you. All right, let's just run through and try and decide order, and then we will pause the video, let you guys give them a try, and then you can put up the answers and check them. Number 6, awards are given for the first 5 finishers. There are 12 people entered in the race. How many different ways could the awards be won? If you're in a race, is it going to matter if you come first, second, or third? Yes, it is, so this is going to be a permutation problem. I'll let you guys do the rest in just a second. Let's read through the next one. Number 7, how many 3-letter arrangements of the letters in the word part are possible if no letter can be repeated? So if it's a 3-letter arrangement, is the word PAR different than the word RAP? Yes, it is. The order matters, so that one's going to be a permutation. Okay, we'll go ahead and pause the video while you give these couple a try, and then we'll look at them on the PDF answer. Thanks. Okay, here's the spoiler alert, so be sure you pause the video because I'm about to put up all the rest of the answers to the questions. I want you to try them first. And there are the rest of your answers to 8 through 13. You can check them and look back over your work and see if there's anything you need to fix. Thanks.